Now we're going to study how the conductors they behave in electrostatic equilibrium. When we are talking about conductors, it means that we are talking about metals, conductors like copper, or good conductors like gold or other metals. Okay, so when these metals they are in electrostatic equilibrium means that no charge carrier is moving. There's no motion of charge carriers inside the conductor. Now let's try to understand a few properties of conductors in electrostatic equilibrium. So suppose that there is a conductor which is neutral and it is kept in an electric field. So this conductor is kept in this electric field, and because of the field, because you know that the electric field is always from plus to minus, so because it's a neutral conductor, initially it's neutral, okay, it has equal number of electrons and protons or the ions. So due to this electric field, the electrons they will move towards this side, okay, and because of this movement, the electrons will create a negative charge here, and because of the deficiency of electrons towards this side, a positive charge will be created on the metal surface towards this side. Okay. Now, because there is a segregation of charge inside, then after some time, no charge will move in equilibrium, and there will be, due to this segregation of charge, there will be an electric field opposite to the external electric field. So inside the conductor, the electric field, these electric fields, they will cancel each other, and therefore the electric field inside a conductor in electrostatic equilibrium, okay, ignore this, it will be so here there is no electric field, so these electric fields they cancel, and the electric field inside the conductor will be zero, with a negative charge on one surface and positive charge on one surface. Okay. Now in this situation, no charge carrier is moving, which is basically electron. Okay, so in a conductor, the electric field is zero at electrostatic equilibrium. Okay, so this is the first condition of conductors in electrostatic equilibrium. Now the second condition is, now if the electric field inside a conductor is zero, so suppose that we are talking about this conductor and it is in electrostatic equilibrium, it has this negative charge on the surface of it. So let us say now that at this point I want to find out what is the charge inside the conductor in electrostatic equilibrium. So at this point I draw a Gaussian surface, okay, and we know that at this point electric field is zero. So from Gauss's law, E vector dot dA vector will be equal to charge enclosed divided by epsilon naught. So the electric field is 0, so the charge enclosed will be also equal to 0. So this is the second condition. The third condition is that the electric field on surface of a conductor is always perpendicular to the surface. So they mean that if you have any conductor, electric field will always be perpendicular to the surface. Okay, so this should be the electric field if suppose the conductor is positively charged. Then now let us try to prove it. Assume that electric field is at angle theta to surface. Let us assume this. Okay. So in this situation, if this is the conductor and we suppose that the electric field is not perpendicular but it is making some angle with the horizontal, then it will have, let's say this angle is theta with the surface. Okay, so if this angle is theta, then this is E vector, it will be E cosine, it will have two components, E cosine theta, and this will be E sine theta. Okay, so if this is true, then this component so it means that electric field will be along this axis. It means that due to this component, charge carriers can move on surface. If you have this component of the electric field, due to this electric field, the charge carriers, it means they will move on the surface. Okay, but we are talking about electrostatic equilibrium. Okay, and when we are talking about electrostatic equilibrium, it means that no charge moving, no charge is moving. Okay, so it means this cannot be true. It's false. You cannot have this component of electric field, and you will have only one component of electric field which will be perpendicular to the surface. So the electric field cannot be at any angle to the surface. It will always be at an angle theta, so that there is no component which is parallel to the surface and no charge will move. Okay. And the last condition for conductors in electrostatic equilibrium is that with the radius of curvature of so if the radius of curvature will increase, the charge density will increase. What does this mean? It means that suppose that if you have any charge it is distributed on a surface like this. Okay, so let's say it has a charge of plus q. If this charge is not like this, but it is sharp, let us say this surface is like this, okay, and so this charge will be all near this point. The charge is still plus q, but the charge density here, it will be larger as compared to this. So as the radius of curvature will decrease, I should say decrease, as the radius of curvature decreases, the charge density will increase. So here, if it is sigma 1, it is sigma 2 charge density. So sigma 1 will be less than sigma 2. These are the 4 conditions of a conductor in electrostatic fluid.